Today we're going to learn how to perform operations with complex numbers. Let's start off reviewing some things we do know about radicals. For instance, how would we simplify a problem like this, radical 18? Well, if you recall, 18 can be rewritten as radical 2 times 3 times 3. This pair of 3's can come out and be written once, and we say 3 radical 2. With the next example, we have a fraction under our radical, which means we can separate our radicals and simplify when possible. So radical 7 can't change, but radical 81 can be reduced to just 9. When we're adding radicals, as long as the number inside the radical is the same, we just add the coefficients and keep the radical. Same thing when subtracting. We are allowed to subtract two numbers with radicals as long as the numbers under the radicals are the same. 4 radical 3's take away 2 radical 3's leaves us with 2 radical 3's. It's kind of a little bit of a warm-up when we're thinking about radicals, because that's when imaginary numbers and complex numbers kind of creep into our way of thinking about math and number systems. Up until this point, we cannot take the square root of negative numbers. It's not possible. So far, we can't think of a number that when multiplied by itself gives us a negative number. So we can't take the square root of a negative number. But these situations do happen when we're solving equations and dealing with things in math. So a while back, they defined this imaginary number. All the numbers we've dealt with so far have been real numbers. But now we're going to add another system of numbers called imaginary numbers. By definition, the imaginary number I is defined to be the square root of negative 1. So I'm going to start with that. I to the first is the square root of negative 1. If you square both sides of this equation, you end up with I squared. And when I square the right side, the square root and the squaring cancel out, and I'm left with negative 1. Now let's think about I to the third. I to the third, I would need to take I times I squared to get I to the third. I is defined as negative radical 1. I squared is defined as negative 1. When I multiply these, I get negative radical negative 1. Let's go to the next one, I to the fourth. I to the fourth could be defined as I squared times I squared. I squared is negative 1. When I multiply negative 1 times negative 1, I get 1. How about I to the fifth? Well, we could get that by taking I times I to the fourth. I is defined as the square root of negative 1. I to the fourth is defined as 1. So I to the fifth would be square root of negative 1. And we'll keep doing this for a while we notice the pattern that's developing. I to the sixth would be I squared times I to the fourth. I squared is negative 1. I to the fourth is 1. So when I multiply those, I to the sixth is negative 1. Do you see the pattern that's happening? I to the seventh would be negative radical negative 1. And I to the eighth would be 1. I to the ninth would be the square root of negative 1, and so on. The pattern repeats every four terms. So let's use some of these numbers as we continue to solve numbers in the imaginary system. When we have a problem like this where we have a negative under the radical, we need to rewrite this as two radicals multiplied together. Negative 1 times radical 28. The negative 1, based on our chart here, radical negative 1, is just going to be I. So all I need to do is call this I. 28 is just like when we were warming up with problems up above. That's just radical 4 times 7. Radical 4 is simply 2. There's a 7 left behind, and an I. But typically when we're writing this, it's not customary to lead with the I. We would write our final answer 2I radical 7. Let's try the next one. Anytime you see a radical that has a negative, simply remove that and put an I out front. That's kind of a faster way than writing it out. Now we're left with radical 32. I is radical 16 times 2. Radical 16 is just 4. I comes down, and a 2 is left behind. So this 16 comes out and becomes the 4. The 2 is left behind, and the I was already out front of the radical. When we multiply numbers like this, we still treat them just like if we were to do negative 3x times 2x. We'd multiply the coefficients and we'd multiply the variables. Even though I is defined to be a number, we still treat it like a variable in this situation. So negative 3 times 2 is negative 6. I times I is I squared. Looking back at our chart, I squared is just negative 1. So I have negative 6 times negative 1, which is 6. When we're multiplying two radicals that have negative radicands, we need to first simplify each radical. So I'm going to take this negative and put it out front and cancel it out. I'm going to do that with both of them. So now I have I radical 12. Radical 12, if you recall, is 4 times 3. The 4 can come out. That's 2 times 2. In fact, I'll go ahead and write this one out in a little bit more detail for those of you that like to break it down into the smallest pieces possible. So the pair of 2's comes out, 2I radical 3. Next, we're going to multiply the next radical, radical 2. When we multiply, the numbers under the radical can multiply to give me a 6. The numbers in front of the radical can multiply. So we have an invisible 1, which will give us 2. And then finally, we multiply these variables, even though it's a number. I is defined as a number. I times I would be I squared. But if you recall, I squared is just negative 1. So I end up with negative 2 radical 6 for my final answer. This is really helpful because now we can use what we know about negatives under radicals and imaginary numbers to solve quadratics, like example number 5. When we're trying to solve for x, we want to get x by itself. So the first thing I'm going to do is subtract 100 from both sides. 4x squared is negative 100. Then I'll divide by 4. X squared is negative 25. Now the only way I can get rid of this square for the exponent is to take the square root and it wipes it out. But if I do it on the left, I do it on the right as well. When you take the square root of a number, you always put plus or minus and then the radical. So x equals plus or minus radical negative 25. But remember, this negative right here can come out and become an I. So what I really have is plus or minus I radical 25. But we know what radical 25 is. Radical 25 is just 5. And then finally, we don't leave our answer with the letter then the number. We change it to plus or minus 5i. Final answer. Let's try another one. Let's subtract 4 from both sides. X squared is negative 4. We'll now take the square root of both sides. X is plus or minus the square root of negative 4. The negative can come out front and be written as an I. I can take the square root of 4, so x is plus or minus 2i. For this last one, we'll subtract 25 from both sides. 5y squared is negative 25. We can divide by 5. Y squared is negative 5. I can take the square root of both sides, which gives me plus or minus negative 5, and just y on this side. But I'm going to take this negative out and make it an I. Y equals plus or minus I radical 5. I cannot simplify radical 5, so that's just my final answer. Complex numbers are just numbers that have a real component and a pure imaginary component. And they are usually expressed of the form a plus bi, where a and b are real numbers. This part right here is considered the real part, or the real component. Then the other side is considered our imaginary, pure imaginary part. So in this example, this would be my real component, 3. 2i would be the imaginary component. 4 is the real component. Negative 7i would be the imaginary component. When we are given a problem that says find values of x and y that make this equation true, what it's literally asking me is to look at the imaginary pieces and set them equal, and look at the real pieces and set them equal. Because if these two numbers, 2x plus yi and negative 14 minus 3i, if these are equal, that means their real parts have to be equal and their imaginary parts have to be equal. So just looking at the real parts, I'm going to pull them off to the side. 2x equals negative 14. What does x need to be so that the real parts are equal? Well, divided by 2, x has to be negative 7. Now I'm going to pull the imaginary parts off to the right. yi equals negative 3i. Again, I'm trying to figure out y, so I'm going to divide by I on both sides. Y is negative 3. So if x is negative 7 and y is negative 3, these two numbers would be equal and this equation would be true. We can take two complex numbers. This is complex number 1 and complex number 2. And we can add them together simply by adding their real parts together and then adding their imaginary parts together. When I add the real parts, I get 5. When I add the imaginary parts, 5 minus 4i, I'm left with I. When you write your answer, it's good to put your real part first and your imaginary part second. Subtracting isn't much different, except you have to remember to distribute that negative. So again, it's kind of like combining like terms. We're going to take the imaginary terms and put them together to get I. And then we're going to take our real parts, our real terms, and put them together to get 1. Multiplying is a little bit more challenging because you either need to FOIL or box. So I'm going to put 1 plus 4i across the top, 3 minus 6i going down the side. And now we just multiply. 3 times 1, 3 times 4i is 12i. Negative 6i times 1 is negative 6i. Negative 6i times 4i is negative 24i squared. But remember what happens here. I squared is defined as negative 1. So I'm going to cancel out my negative, because this is really negative 24 times negative 1, which is positive 24. I have some real terms, and I have some imaginary terms. And when I combine my like terms, I end up with 27 plus 6i. You can also type that on your graphing calculator to check it. You could type parentheses 1 plus 4i. I can be found by pressing second and the decimal point, and then multiply again 3 minus 6i. You get 27 plus 6i, which is exactly what we got using the box method. Go ahead and pause your video and try letter B. I did not use the box method for this one, I just FOILed it and had my inner and outer terms, which combined to negative 9i. Plus 10i squared is the same as minus 10. 2 minus 10 is negative 8, and then the imaginary part. Just like you're not allowed to divide by 0, you're also not allowed to have an imaginary component or an imaginary number in a denominator. When this happens, we need to multiply by what's called a complex conjugate to eliminate that complex or that imaginary part that's in the denominator. A plus bi and a minus bi are considered complex conjugates. It's not strictly the opposite, but you do change the sign in between the real and imaginary component. So the complex conjugate of 3 plus 2i is going to be 3 minus 2i. And I want to multiply by this on the bottom. So in order to do that, I have to do the same to the top. That's the rule. The rule is if you want to multiply by the complex conjugate on the bottom, you do the same on the top. On the top, I have 5i, 3 minus 2i. And on the bottom, I have 3 plus 2i times 3 minus 2i. On the top, we're just going to be distributing. It's not too bad, right? 5i times 3 is 15i. 5i times negative 2i is negative 10i squared. On the bottom, again, you'd either need to use the FOIL method or the box method, especially when you're starting out. Now, eventually you're going to notice patterns. You're going to start to see that you don't actually have to write this out each time. You're going to notice that the middle terms will cancel out. Remember, I squared is just a negative, so that makes it a plus 4. So I end up with just 13 on the bottom. But we still need to clean up our numerator. Again, I squared is just a negative 1. So negative 10 times negative 1 makes positive 10. And we like to put our real part first, and then our imaginary part second. That's one way to write it, or we can write it like this: 10/13 plus 15/13 I. Final answer. In the next example, we don't need a conjugate because we don't have a complex number in the denominator. We have a pure imaginary number in the denominator. So the only thing I need to do to get rid of the I is to multiply by I over itself. In the numerator, we can distribute, and we get 5i plus I squared. And in the denominator, we get 2i squared. All of the I squareds are just negative 1. So I end up with negative 1 for my real component, plus 5i for my imaginary component, over negative 2. Further simplifying, negative 1 over negative 2 is simply 1/2, and then minus 5 over 2i. Final answer. So complex numbers really aren't too bad to work with, but it's super important to be able to function with our imaginary numbers so that we can use them when we're continuing to solve quadratics. One last thing I want to point out, scrolling back up to our notes, what if we have I to the 45th? Well, instead of continuing this pattern over and over and over all the way until I got up to I to the 45th, just divide 45 by 4. Or think, what's the number closest to 45 that's divisible by 4? That would be I to the 44th times I. I to the 44th is just I to the 4th 11 times. So this part would just be 1 times I, which is I. So I to the 45th is I. That's another way to think about it. Just follow the pattern. If you do 45 divided by 4, you get 11, remainder 1. And that becomes your exponent for your answer. Let's try another one. Let's try I to the 39th. Well, if I do 39 divided by 4, that goes in 9 times 36, I'd have a remainder of 3, which means I'd be basically saying I to the 3rd times I to the 36th. I to the 36 would just be 1, because that would 4, 8, 12, 16, and so on until I got to 36. That would just be 1. And then I to the 3rd tells me my answer for I to the 39th is just negative radical negative 1.